Right. Let's start. Thanks for inviting us. So today, me and Ilya present our solution that took the first place at Behavior Challenge that was organized by Stanford and was a part of NeurIPS just in the last December. So it's quite fresh. So how we will structure today? I will start with telling you a little bit about the challenge itself, what was the task. Then Ilya will tell about what we actually did, what kind of model we trained, what heuristics we used, and then I will get back with the results of actually when our model succeeded and when it fails and why. Regarding the question, please ask them in the chat. We will try to take them as we go, and but may take some of them at the end. All right, let's start. So a couple of things about us, because I think it's interesting. So we are kind of independent team. We didn't know each other 3 months before the competition, and we totally separated geographically, and like even haven't seen each other. And it was like the whole work was fully remote and asynchronous. Given that we're distributed between Thailand, India, and UK, and the kind of Stanford is Pacific time, the sun never set upon our work, and we basically worked on 24/7 last 2 months before the competition. All right. So regarding the behavior challenge, what was the task? It was the challenge in the simulation, and it was based on Omni-Gibson, which is kind of a fork of NVIDIA Isaac Sim. So you can think of the NVIDIA type of physics. The challenge itself contained 50 household tasks. Imagine what kind of robot need to do in the household to help humans. And it was all tasks were surprisingly long horizon. So average duration was more than 6 minutes, but some tasks span for more than 15 minutes, which is kind of rare in the robotics datasets. The dataset was pretty significant because each of 50 tasks contained 200 demonstrations. So in total, we have more than 1,000 of hours of teleoperation data. And the metric was simple, just binary or partial success. So basically, there is a specific language that describes how far robot advanced toward task completion, whether all objects in places, etc. So regarding the tasks, as I said, there's 50 of them. They kind of diverse. Here's the example of one of them, where robot needs to prepare lunchbox. And you see it's some kind of combination of pick and place, but there's multiple objects. Some of them a bit harder to reach. Robot also need like go to the fridge, open the doors is very common sub-skill, close them. And if it's, for example, if the robot is not closing the door, then it will be kind of get less partial success. So in total, skills are navigation, search, opening and closing the doors, pick and place object, pushing button, interacting with object, etc. And here's another example when robot needs to navigate from one room to the other and pick a box and bring it back. And beside the task name, which is moving boxes to the storage, in this case, there is an instruction. And for example, in this case, instruction says this: move the 2 storage containers from the living room to the garage, etc., etc. Which actually not strictly needed because there's 200 demonstration which describes what needs to be done. So it's more like for human to understand what's happening. Other task examples include like slicing vegetables, and you see that physics is still not ideal, but nonetheless interesting. Washing stuff, which is mostly just pressing the button on the washing machine, or finding the object. Like in this case, where you need to find spray, and stuff like this. So this is tasks. Now, how the solution got evaluated? As I said, there is 50 tasks, and each of them have 200 demonstration. So this 200 demonstration was sampled from randomly generated object placement and initial robot placement. So for each task, you can vary where the object's located and where the robot's located. But the object and the environment stays the same for the same task. And for public score, for kind of validation, organizers then give you 10 additional instances which are sampled from kind of the same distribution. There's some caveat, but we can say from the same distribution. And you can verify your policy on them. And for final private score, organizers have had a holdout set of 10 more instances that we don't know about, like kind of initial placement of objects, and they evaluated our model on their side. And as you can deduce, there is, regarding generalization, there is like partial generalization. So robot cannot assume where the object would be or where robot itself would be in the beginning. But there is no need to generalize across language or some kind of logic, because the tasks are always the same and the objects are always the same. And last piece about evaluation, it's pretty substantial amount of tasks. So it actually takes a lot of time. If you just run it on the single GPU, it would take probably 10 days, around 10 days. Now, I know a lot of people, me including, a little bit skeptical about evaluation, about simulation. But actually, the whole behavior kind of simulation is based on the work on real-world robots, and the robot is the same, the liberation model is the same, tasks are mostly the same. So it's kind of showing that it's not just like kind of toy example. It's based on the real-world task, and from that side, it's quite good. You can check out more from Stanford how they actually done it. Regarding how they collect the data set, it was collected by multiple teleoperators, and one note, it contains a bit too much idealized demonstration. So there is no recovery, nothing like this. So if the teleoperator would fail at some point, they will just roll back and repeat the same sub-step. And it make a little bit of too idealized, too pure demonstration that if you kind of can imagine span too narrow subspace in the all possible trajectories. All right, now Ilya, can please continue to the method.
Yes, give me a second because I need to reshare the presentation to be able to control it. And I hope you can see it now. Okay, yeah, so let's discuss the actual model and actual approach that we used. So first of all, we started from Pi-05 as a baseline. So Pi-05 is a VLA model developed by Physical Intelligence, and it's probably one of the best open source VLA models right now that's available for fine-tuning and has both code and weights open sourced. And overall, this model kind of consists of few main parts. So the biggest part of it is LLM part, that is basically Gemma, and then it has image backbone that is SIGLIP. If you combine SIGLIP and Gemma, you get VLM that's called PolyGemma, and it's trained together. And then basically they took this PolyGemma and added a couple more, made some small changes in architecture, also added two types of action outputs. One is fast tokens, is like tokenized robotics actions, and another one is extra transformer that is called flow matching action expert, and it uses flow matching approach to transform some random noise into the action chunks. And yeah, so this model is available in kind of pre-trained form, where it's pre-trained on the like hundreds or even thousands hours of different robotics data for different robots, different embodiments. And Physical Intelligence in their demo basically shown that eventually this model is capable of completing tasks that are very similar to behavior challenge, and they shown that it works even in real life with real robots. So this is why we decided this is like a good baseline to start from. And but we didn't just train this model as is. We implemented a lot of changes to this model, both in architecture, in training, in the inference, and basically different stages of the kind of usage of this model. So some of these changes, the biggest one is system 2 that we added to control where we currently are in the process of completing the task. Then we actually completely dropped all the text understanding and all the text inputs because, as Gleb already presented, in this challenge, we deal with fixed set of 50 tasks, and we are not asked to generalize beyond it. We are not asked to follow all the language commands that user can have. So basically, instead of using text prompt as an input, we simply train 50 embeddings one for every task, and it kind of successfully replaced it while using kind of less tokens for task representation. Also, we changed the way how this action expert attends to the main VLM part by training the mixed layer attention in this case, and I will talk in more details later how it works. Then we also introduced the knowledge about actions correlation to the noise that we use for flow matching. Then we kind of improved the training process by running multiple action expert steps for each VLM step during the training. And then finally, we implemented a couple of changes for inference. So first of all, we use some sort of in-painting to make sure that all the action chunks that model predicts are connected, and the robot eventually have like very nice and smooth trajectories that we're predicting. And the second, we speed up execution of this trajectory. So we basically made our robot to move 30% faster. That allows to also solve more like problems in the same limited time. I will talk about most of the things on the following slides in more details. So I guess, yeah, maybe it's not everything clear what I'm talking about right now, but I will try to explain what exactly was done for each of these points. So before I go there, just a couple more more like facts. So first of all, we used as an input only 224 by 224 RGB images and proper states of the robot. So proper state is basically the position of every motor that this robot has, and this robot has 23 motors. In the data set that originally was provided by organizers, there were also depth images, so you could use like the depth representation on top of RGB, and they also provided instance segmentation images already kind of pre-computed that we could use, but we didn't use this extra data. Another extra data that we didn't use is extra subtask annotation. So it also was provided in the data set. So basically for most of the tasks, they kind of split them into separate subtasks, like move to the table, grab this object, move this object to some other place, and so on. And there was this more detailed annotation, but again, we also didn't use it, and we achieved the results without this extra annotation needed. A little bit about the predictions. So we predict delta actions from our model. So we don't predict the final position of the motors. We predict the relative change of every motor position in the robot. And also we apply timestamp normalization. So this is kind of technique to make sure that robot is not focusing too much on the actions that are in the farther future. And at each step, we predict one action chunk of length 30. So it means that we predict like next 30 positions of all the motors where the robot should move. Okay, so now let's go to the more kind of complicated part. So first of all, let's talk about how we help robot to resolve some unclear cases. So these are two frames from the same episode from the training data from the problem where robot need to cook the popcorn in the microwave. And one of these images is from the very beginning of the video where microwave is empty, and the robot's supposed to go there and open the microwave. But the second image is from the end of the video, where popcorn is already inside, microwave is closed, and the next action should be to click the button and start the microwave. You can kind of take a few seconds and try to guess which one is where. And I will actually just show you the results now. But the main point is that it's actually not obvious, and it's pretty hard. And also, kind of both of this image kind of can be representing, can be like from the beginning and the end of the video. And also the policy that we use uses lower resolution images eventually, so it's even harder for the policy to understand where it is right now. And also the policy doesn't have any memory, so it doesn't remember what it already has done in the last minute. So the only the main source of information that it's relying on is the current image. And many problems have the same issue, that two different like frames, or even many different frames, can be very similar, even so they're in very different parts of the problem. And to resolve this issue, we introduced System 2. And overall, System 2 is like, I think recently, in the last like year or couple of years, maybe became very common way to resolve this problem, and also add some reasoning to the VLA policies and robotics. But generally, this System 2 means that you have another probably VLM model on top of your main VLA that is run with much lower frequency, and that, for example, try to evaluate what's happening right now, uses some memory, trying to decompose the task into multiple steps, and so on. And it's pretty not trivial how to train these models and how to use it. So we kind of looked at the task, and we understood that, again, we can utilize the fact that we have only like 50 fixed tasks, and we shouldn't generalize beyond these tasks. And it means that we, instead of kind of planning and like creating the plan of the task each time from scratch, we can just take the training data and somehow like average this data, split all the episodes into steps, and say that, okay, every time when you complete this task, you need to follow more or less the same steps. And this is what we did. So we took like every episode in the training data, we split into like from 5 to 15 equal stages, depending only on the time of this episode. So for the short tasks, we split them into 5 stages. For the long task, we split them into 15 stages. And then we added the number of the stage at any point when we make the prediction, both as the target, and the input for our VLA. So basically, our VLA, first of all, can look at the pictures and try to predict what is the current stage, what is the number of the stage of the for this particular moment for this particular task. And on the other hand, we like a bit later, we send the stage as an input to this VLA, and it can use it to predict actions. You may ask, isn't there like any leakage if we use the same kind of number as a target and as input? And no, there is no leakage, because we kind of isolate them using attention mask. And you can look at this attention mask matrix represented here. So it has kind of block structure for our model. And the first block that basically takes only images and the task embedding. This is the part of the data, part of the input data that is used to predict the current stage. So we use only images and task embedding to predict the current stage. And then we have like some other inputs that kind of included in the next block of this attention, and they already and the stage, the actual stage that we provide as an input, included only here. So basically, so at the moment when the model predicts the stage, it cannot see the stage that is supplied as an input. And then, as I said, we have like these 2 representations of actions that also can kind of attend to everything, including the stage in the input. So this is how it's kind of trained, and what we do during the predictions. So we simply start our System 2, start the tracking from 0, because every time we start to complete the task from the very beginning. And then every time when we predict the action chunk, we also predict the current stage. And this predictions goes to this System 2, and System 2 applies very simple filtering. So it just increment this stage one by one whenever we predict 2 times out of 3 latest predictions, we predict to increment it by 1. So basically, if you're at stage 1, you can only move to stage 2 if your model starts to predict that you kind of already moved to stage 2. There is no way for like you to jump from stage 1 to stage 8, for example. And this kind of filtered and filtered predictions of the stage then provided back to VLA as an input during the next prediction. So whenever we predict actions, we use only this kind of correct stage that already filtered from all the possible mistakes. Let me give you the example how it works. So on the left, you can see demo of the simplest and shortest task in the data set. It's called turning on radio. So basically, robot should go to this table, grab the radio, click the button, and put it back. And in this case, you also can see that when robot lifts the radio from the table and when robot puts it back, it looks pretty similar. Yes, so just one arm holds the radio, and it can be both like framed from the beginning and from the end of the episode. And this is exactly where confusion happens. So on this chart on the right, you can see the predictions of the model regarding the current stage. And in the bottom, the red line is the raw prediction of the model. And the blue line is this filtered prediction of the system 2. And this is the like most interesting area around like step like 1000. So this is exactly where this confusion happens, because this is the beginning of the task. So most probably a robot lifted the radio somewhere here, and the predictions started to jump between like, I don't know, 1, 2, and 9. So 9 is the stage when it usually puts the radio back. Like 1, 2 is the stage where it usually like lifts its up. And without system 2, it would be like very, very confusing. You can see like every second, every like prediction, robot actually changes the prediction of the stage. And it's very, very confusing. But after we filter out everything and let it go up only like one step at a time, everything is much better. So now at each prediction, we send this like stage 2 as an input to the model, and model knows that it's currently still in the very beginning of the task, so it needs to leave the radio rather than putting it back to the table. Yeah, so this is a very kind of big thing that helps to resolve this non-Markovian states, where the information from the observation is not enough to understand where it is right now. And another big addition in this system 2 is correction rule for the gripper. So also Gleb already mentioned that the data set that's provided is extremely clean. So this data set doesn't have failures, it doesn't have any like recovery, even like it doesn't even have like a small mistake. So all the episodes in the training data are very, very clean. And it means that whenever we start to really roll out the policy and policy makes a small mistake, it have no idea how to recover from this mistake. And the most common mistake that we've seen is closing gripper whenever it tries to grab some objects. So for example, it tries to grab some vegetables right now, and it closes gripper. And in training data, it never seen the like reopening of the gripper in this case. And it doesn't know that it can simply reopen the gripper and try again. And it can waste like many minutes, or sometimes even just all the time that we have for the episode, and just go around with this closed gripper. Even so, it could reopen it again in 1 second. So what we did, we added very simple rule that works on top of the policy, and it checks if the gripper is closed at any particular moment. And if the gripper left or right is closed, but this particular gripper was never closed in the training data for the same task in the same stage of the same task, then we simply reopen the gripper immediately, because most probably it's just a mistake and we like accidentally close the gripper. And it works very well. You can see in this video on the right, whenever gripper is closed and there is nothing there, it's immediately reopens it and gets kind of spends like 1 second and then tries again. So it kind of gives our policy much more retries than without it. And it actually had a very significant effect on our final score. So for the task, especially that have a lot of this like picking, grasping, and so on, we get up to x2 increase in the success rate and the Q-score. This is very, very big boost for the result. Okay, so this was about the system 2 and this correction, and the next big change.
I think there's a couple of good questions in the chat.
Okay.
So first of all, just want to highlight that system 2 is basically heuristics, just to simplify the process, as Ilya mentioned. So it's not a separate model as you see sometimes. And second, there was a good question about when the error occur. Are they because kind of VLA not listening to the input or from the stage, or because the stage is incorrect, predicted incorrect or filtered incorrect? And this is a great question, but we unfortunately don't know answer to it. Maybe in some future work we will analyze it. Thanks.
Yeah, you can just I can give like overall a big comment. So in this competition, we were like very, very restricted in terms of the time that we had for competition and the resources. So we focused a lot on the optimization of the actual solution and getting like high score, but we really didn't invest too much time in like ablation. So we don't really, for some of the ideas, we kind of believe that they worked, and we like tested them on the small subset of the data, but we don't have like very statistically significant proofs that something works, or like very deep analysis of the results of some of the changes. So yeah, this is like important thing to mention here. And also there is a small question for the gripper.
There's one.
Let's just read. So for the gripper correction, do you access the training data during rollout? No, so we just pre-computed it. So we basically looked at all the training data and simply created the list of tasks and stages in the tasks where gripper should never be closed.
But to some extent you can say that.
And it's like very, very simple check during the inference.
Yeah, but to some extent you can say that we access this training data, we just compress it into this list. So we do have this information, but just in a very small way.
So thanks. We don't need to iterate through all the like 1,000 hours every second and so on. So it's just very simple, like dict whatever that we go through and check whether it's allowed to close the gripper at any particular moment or not. Okay. So I think I will continue is the next topic, and the next topic is the action correlation that impacting how flow matching works and how we fix it. So again, a reminder, so we predict all the actions in chunks. So we predict a chunk of 30 actions every time when we run the model. So it's kind of 30 steps for the model. And also each action is the position or like change of position for 23 motors that we have in the robot. So basically, every prediction of the model is some kind of like matrix that has 30 by 23 dimensions. If we like flatten this matrix, we will have like 23 multiplied by 30, 690 degrees vector. And this is like one prediction of the model. And what we can do, we can just look at the correlation between different dimensions of this 690 degrees vector, and we will get this matrix on the left. So this matrix has this kind of block square structure. So every square here that you can see, and you can see this grid like 23 by 23. So every square represents some combination of two dimensions of the robot, or like basically two joints, two different motors of the robot combination. And if you go inside any of these squares, then it will be like 30 by 30 square that basically represent timestamps inside the channel. And so, for example, everything that you can see on diagonal, all these like red squares, they represent the kind of time stamp correlation between the like predictions for the same dimension. So you have like one motor, you look how this motor position changes during these 30 actions, and then compute correlation between them, and you get this like red square. If we simply average all the red squares on diagonal, you will get like this red square, big red square on the right, and you can see that the correlation along the time is extremely high. So like actions are very, very, very correlated, because you can think about it. So for example, if robot moves forward for a few seconds, during this movement, I don't know, the velocity of the motor that's moving its forward will be more or less constant. Or, for example, most of the time the gripper is either closed or open, so it's like completely constant value for them, and many other joints, they stay in the same position for a long time until you really start moving them. And even when you move, you usually move with some linear speed and so on. So there are a lot of correlation, especially in this short period of time that represented by one chunk. And also there are some correlation between dimensions. So for example, this 3x3 square represent the 3 motors in the trunk of the robot. So when the robot kind of moves the body forward, backwards, up, down, and so on, there are 3 motors that usually are moving together. And then also you can see some outline of square over here in the middle, and another square over here. These 2 big squares represent the joints of the arms. So I think it's left and right arm here. So yeah, you can see that some of these dimensions, and especially in the time, are very, very correlated. So we have very strong correlation between the sections. And it actually creates a few different problems. And some problems can be specific for the model type that you use. And in our case, we use flow matching. And it creates a very specific problem of, I would say, uneven distribution of difficulty of flow matching steps. Let me try to explain what it means. And to do it, I generated very, very extreme artificial example. So it's not the real data, but it's very extreme example that helps to understand it easily. So let's assume that we have only one dimension. So we basically predict only position of only one motor. Let's say we have only one motor in our robot. And the correlation between our predictions and the training data is extremely high. So I use 0.9999 correlation between any 2 adjacent actions. And it means that with this correlation, so whenever we look at 30 predictions, 30 steps action chunk, it will be more or less horizontal line without much variance. Again, this is extremely artificial example just for demonstration. It's not exactly how it happens in the real robot. So then we apply flow matching. And I'm expect that you know, at least in the high level, how flow matching works, but I will explain overall basics. So flow matching is basically the process that where you train the model to move some random distribution into some target distribution. And when we go look at the sample level, then we have our target signal that is shown by this green line. And then we start from completely random, uncorrelated noise that is shown by the red line. And then at each step of training or inference of the flow matching process, we send the noisy actions that is basically just weighted average between our final signal and original noise. We send this blue line as an input to the model, and model tries to predict these vectors, these light purple vectors that basically give you the velocity that you need to kind of apply to the noise to eventually go to the target signal. So it kind of predicts the direction and the speed of movement from the red dots to the orange to the green dots, using the blue dots as an input. And yeah, so ideally, kind of in ideal case, we want our model to look at, let's say, pictures and images from the cameras or some other inputs that we have, then kind of condition based on these inputs, these observations. We want it to predict some reasonable velocity that transforms any random set of numbers into the good actions for this particular case for this robot. And it's kind of fine when we start this denoising process, and this process usually done in a few steps. So we make like one prediction, we move toward predicted direction, then we make another prediction, move a little bit again towards this direction, so on. So when we make our first steps, everything is fine because we start from the complete noise. So the only thing that model can do it should really rely on the observations and try to really predict what the kind of good actions would be in this case, and kind of predict some like velocity that moves us towards this action. So there is no other way for the model to make a reasonable prediction except to really learn what we want model to learn. But when we look at the one of the final steps of the flow matching process, in this example, when we like already kind of recovered signal by 80%, and our input is like mostly real signal, but with like 20% of the original noise, then this correlation that we have in data starting to like break the training process. And the problem is that if we know that our correlation between like target actions is very, very high, so that this green line is basically almost horizontal, then instead of trying to predict something complex, instead of like looking at the like images, instead of like really doing what we want our model to do, we can simply average all these 30 blue points, and then maybe like scale it by dividing by 0.8 in this case, and we will get this very nice estimation of the actual signal. And again, we model don't need to know anything in this case about observations. It doesn't even need to learn anything what we want. The only thing that model needs to learn in this case to be able to do it is the correlation between actions. So it's kind of very, very strong like shortcut for the model. So instead of learning some reasonable stuff, let's just apply simple like filtering, smoothing, averaging, whatever to the noise, and we will get a very good prediction of the signal. And usually when deep learning models have shortcuts, they use these shortcuts. They like don't go the hard way. They don't learn the stuff that you want them to learn. They just learn the shortcut. In the cases when the correlation is lower, so for example, I generated like lower correlated actions on this slide, we cannot apply this like simple averaging. We cannot use horizontal line, but again, you can apply some smoothing or filtering or something like that to the blue line without learning anything about actions, but using only the correlation information. And again, you will have, this is more similar to the real life example. And in real life, if our model is smart enough to simply remember the correlation between target actions, it will utilize this correlation and use all these shortcuts instead of learning what we want. And eventually, it just means that if you have, I don't know, flow matching with 10 steps, first steps of this flow matching will be very, very hard for the model, and all the like main like predictions will happen there, and the last steps will be completely useless. It's just some filtering, and we don't want it to happen, and we think this is the problem that we need to solve.
Yeah, sorry to bother you. Could you please finish in 5 minutes so we'll have some time at the end for the questions?
Yeah, sure. So this is the problem, and our solution is actually very simple. So for the solution is instead of using the random noise, let's use the noise that has the same correlation as the our actions in the training data. So just to summarize, so we, instead of using the random noise as in the original flow matching, we generate this noise from using the correlation that our actions have. One small addition, we regularize it a little bit because it is more numerically stable if you do it in this way. Okay, so this is another big thing, and let's talk about the next big change. Is the change between in the way how we do attention between the action head and VLM. I will try to go through it like very, very quickly. So so basically our model consists of two big transformers. One is VLM, another one is this action head. And there are multiple ways how this second transformer can look at the first one. So the most classic one is to look at the output of the first transformer using cross attention. Then there is like another approach that used in some other VLAs is cross attention can look at some internal layers of the VLM. And finally, there is like approach that is used in the Pi-0 and Pi-5, when that is also taken from the mixture of expert architecture, where it's not really a separate transformer. It's just the continuation of the first transformer from the main VLM, and it applies the kind of combined cross and self-attention in one go using like separate set of weights. And the thing is that all these three approaches are used in different VLAs nowadays, and there is no really conclusion which one of them is the best one. So what we did from our side, we decided that we don't need to choose one of them, and instead we can simply let the model to learn any logic that it wants. So what we do instead in our model, so we allow every layer of this flow matching transformer to simultaneously attend to the linear combination of all the layers of the VLM. And the weights of this linear combination are trainable parameters. So basically, we let our model to learn whatever it wants. So if it wants to attend to the last layer, it will attend to the last layer. If it wants to attend to some layer in the middle of VLM, it will attend to this layer. If it wants to completely ignore all the VLM parts and work with the self-attention, it can also achieve it with some combination of these weights. And yeah, so this is what we apply. We believe that it gives like more flexibility to the attention inside the flow match. Okay, so this is, I probably like skip this one is like simple improvement and just finish about discussion about the inference optimization. So I think the big thing that we added to inference optimization is in painting. As again I said multiple times, we predict action chunks with 30 actions in each, and each prediction is done independently. And in general case, this two chunks can be very disconnected, and model can, for example, be very undecisive what it should do at any particular moment. So to fix this problem, what we do when we predict these two consecutive chunks, we kind of create some overlap between them, consisting of 4 actions. And whenever we predict one chunk, we execute only 26 first actions of this chunk and use the next 4 actions as an input for the next prediction. And then apply in painting logic, similar to what is used in image generation, when you can kind of ask image model to replace some part of the image. Exactly, basically the same math behind it. We apply it to predict the next chunk, such as first 4 actions are very, very close to the last 4 actions of the previous chunk. And also, we remember that there is some correlation between our actions, and if we completely ignore it, then there will be a big break between step number 4 and step number 5. And to avoid it, we also add this kind of extra correction that uses information about correlation between the actions to make sure that the whole prediction is very, very smooth. Okay, so I think this is the main thing that we introduced for inference. Another quick thing that we simply execute all the actions 30% faster, but again, I will not spend time explaining it. And yeah, the final slide before I give it back to Gleb for the result presentation is that we did all the training on the 8H200, and the pure training time of our model was around 1 month. And the total budget for this competition for our team was around 13,000 USD. Out of them, 10,000 was sponsored by NeurIPS, and we used it for the main training run. And then around 3,000 extra we spent on different experiments, evaluations that also take like a few days, and so on. So yeah, I think that's it about the model architecture, training, and inference, and we can move to the results part.
Yeah, Ilya, there is a very good question from Berkay. Apologies if I mispronounce, but it's about this correlation between actions, especially across time. Can it be addressed with masking? And we have seen that several papers recently where actions masked randomly to prevent attending later action to the earlier action in the chunk. Do you think would it be would it solve exactly the same problem, or is it still the method that we developed is?
I would say it's like slightly different. So as I said, that the correlation between actions actually generate multiple different problems, and yeah, one of them can be prevented by this masking. But masking also create like some other problems because we want to predict like consistent chunks. So we want actually these actions to attend to each other and be predicted together. So it's like nice and smooth trajectory. There are also other ways to deal it, and actually partially physical intelligence address it in the original Pi 0 and Pi 05 because they sample the like different time for flow matching during the training with some specific distribution. So they already pay much more attention to these first steps of flow matching during the training. So yeah, there are like multiple steps that you can apply to it. I think that yeah, you can also like just move to white in space. So there are like many kind of approaches that you can apply, and they solve slightly different problems. But yeah, I think in our case we kind of solve differently this this problem by this shift. But yeah, like this kind of masking and can work in other cases. For example, if you predict it as separate tokens and so on. There are definitely some VLAs that use similar approach.
Yeah, great, thanks. All right, I will speed up with results. So this is just a copy from leaderboard. So our final score was almost 26%. It means that including partial successes, we successfully solved roughly a quarter of all tasks. And you see that NVIDIA's search team was just behind us. I don't even think this is statistically significant, but I'm still very pleased that we took the first place. The other team is substantially behind. And again, note about ablation and finding in our solution is that we done some small scale experiments, but obviously as an independent team, our budget was significantly constrained.
Sorry to interrupt. Are you sharing the screen with the results?
Yes, Ilya, do you see?
I'm just seeing.
Yes, we can see it.
Now I can see it. Yeah.
We see it.
Okay, cool. Let me know if there will be problems. So some validation that at least combination of our method was right comes from that the second team from NVIDIA spent probably 1 or 2 orders of magnitude more on the compute because they trained the model for each task and also done extensive RL gathering style data collection and simulation. Okay, so the results, as I said, 26%, and the public and private score almost identical. If we talk about binary success, it's 12%, so it's kind of half of our score comes from task fully completed and the other half from partial successes. And if you look into all 50 tasks and for each test episode where it was evaluated, you can see the picture as follows, that dark green is fully successful tasks and fully successful episodes. And some tasks have quite a significant number, more than half of fully successful episodes. There is a lot of partial success, but there's also some tasks that are failed completely. When we look into them, it's not that they are super complicated, it's just that model need, for example, do some very precise movements, and it slightly fails. I don't think it's kind of inaccessible. I think with just a longer training, slightly more accurate data collection, etc., it would be able to succeed in this task as well. Now, some example of successful runs, as you can see here, is like model need to cook hot dogs, so it's kind of struggle a little bit to pick the first one, but because it's imitation learning, which is very well known for kind of retrying, it's eventually managed to do this, and it execute the whole sequence successfully, like 3 in 1 arm, opening the microwave, going back and forth. So all these actions should be implemented in the correct sequence, and it managed to do this. Another successful episode is where the model needs to pick up trash. And here's this, like, find 3 cans of soda. And as you can see right now, if you look precisely, you'll see that because of the strange physics, the kind of bottle jumped, can of soda jumped and rolled into the corner, which presented like super hard challenge for the model because there was no such data in the data set whatsoever. And it struggled a lot, but eventually it succeeded and also scored full success on this episode. Also, some notion about model recovery, which is kind of crucial to this competition and the whole field, is that if you look at the model that was trained on only one task, when it dropped the picture or other object, it does not attempt to recover at all. It's just like, I never seen that a human operator dropped the picture, so I would do nothing. And in comparison, when we train the model on all the tasks for sufficiently long, it also dropped the picture. But surprisingly, it started to actually attempt to lift it from the floor. And as I said, there was nothing like this in the training data set. So kind of model learned to decompose various aspects of the task and learned that in some tasks, it's actually was picking something from the floor. So probably I need to pick this picture. And this like kind of super cool emergent behavior from cross-task learning. Why we still fail? And I say that we succeed in quarter of the task. So 3/4 is still kind of a lot of problems. We label 15 tasks out of 50. And the leading cause is dexterity, which is basically the model is still kind of clumsy. It's not picking something or dropping items. The next in the how often the reason why model fail is that it do some kind of error related to sequence or decided to finish early. So it's kind of not fully understand what need to be done next. And we do have system 2, which allow us to disambiguate between, let's say, start and the end of the task or middle and the end, but it's not probably sufficiently powerful and fine enough to separate close stages. And the third most common failure case is just confusion. It's just mostly my confusion during the labeling, and because the model just started to behave very weirdly, probably because it got into out of distribution state and the action are quasi-random. Let's look actually at this example. So some bad dexterity is where the robot is knocking the picture, and again not able to pick it up. So you can see that like kind of recovery is not magically working all the time. Some other example again of bad dexterity is this task where the robot needs to slide this box and then pick it from the side, which is kind of very complicated, and it sometimes just drop it. Regarding the order sequence, you can see that here robot successfully picked 2 cans, and then it decided that it's done. But the actually third can is just on the left. It's not in the picture, so it's very hard for a robot to understand what's happening, and probably system 2 fails at this moment. And regarding the confusion, loading. So in this task, the robot can really struggle to place this box, and it's very speed up because it's happening like during 10 minutes, and finally it was able to place this box, but then it just do weird behavior, and ultimately it decided to escape, try to push through this door. Why this happened, we have no idea. This task actually fully failed. I looked into training data. I haven't seen any problems, and interestingly, that after some time, model even tried to try the door handle. Also, some other confusion from this task. Model decided to sit behind this desk, and I cannot explain this because there was nothing like this in the training data set. So it's kind of trying to sit behind this desk, which is super funny. But this is the price for using end-to-end solutions, where we kind of very hard to diagnose black box problems. So what give me some actually positive vibes is that if you look at the problems and how would you try to solve them, you would say that, oh, we just need bigger, better VLA models. We need system to better understand what we need to do next, and we need more diverse training data set to widen our manifold of where we know what actually to do. And this is exactly what top AI companies in robotic space are doing right now. So in that sense, failures that we see in this competition are exactly the failures that you see in the reward, except hardware-related stuff. So it's kind of saying that this competition is actually pretty good to work towards the better AI system. It's not just a toy problem in itself. And also, as I said, our model scored only 26% success rate. So there is so many things still can be improved. Just lastly, the slide with all our contacts, I would really encourage everybody who is interested in why model failed, look in our website, because there's a ton of videos with labeled videos of why it's failed. Ilya prepared just a very, very clean and accurate, just brilliant code, how the solution is implemented. You can easily reproduce it, and everything is open. Benchmark itself open, simulation is open, our code is open, so you can train it and see for yourself. There's also tech report and the challenge itself. And also, yeah, again, thanks for our sponsor neighbors who sponsored our training effort. Yeah, I think that's it. Ilya, do we have some questions?
Yeah. I think. So I think we can discuss like questions more, and also I think there were some questions before when I was presenting that I think actually were covered eventually in my presentation. But if you think that we didn't answer, please ask them again. And now you can, I think, just turn on your mic and ask. Yeah, there was like there is one more question about. Yeah, about this like single task optimization and other things. And if we supply additional action frames to a single task, do you think this can be learned recovery trial? So yeah, I think that in this particular problem, we had like very, very clean data set, and it's very bad for robotics, to be honest. So I think that for robotics, it's much better if you have like some fails, if you have, especially you have some recovery, because then your like coverage of potential states and what to do in this stage is much, much better. So the problem with this particular data set is that it's extremely clean, and when you like roll out the actual policy that you train on this data set, it will make some mistakes, and the small mistakes will accumulate, and eventually you go very far out of distribution, you make some like mistakes, and you have no idea how to recover. So yeah, like one approach to solve it would be to just add either like fails or recovery data to data set, and I think it will be much, much better even with like a little bit extra, like extra 5% of recovery probably will improve the results a lot in this problem. Another ideas that we wanted to try but we didn't have enough time is RL. So you can do it with reinforcement learning. You can just roll out the policy many times and wait until it makes it to complete the task, and then use it for extra training and so on. So yeah, like this is definitely something that will it will help in this task. And also we can see like in other labs, like in the again physical intelligence, recently released the next version of the SPI-06 star model that they train with RL and achieve even significantly better results than Pi-05. So it's another approach how to solve this problem.
Yeah, I would. There is also a question that if you just include failures in the data set, yes, if you just include them, that would be bad. But if you label them as failures and you use data only after them, so how you recover, that's completely different story. There is also a question about using some techniques from pick and place anything paper, and I believe this is a recent paper. I saw it, but I already forgot what's there. So if you remember, or Nahida, if you can provide context.
Also, like I remember this. I remember this paper, but I don't remember content, to be honest. So I definitely heard this paper, but I don't remember details about this paper to comment about it. But yeah, we also discussed about improving the like separating actually process into like multiple steps, whether we should separately do like navigation and pick and place and train separately model for pick and place and so on. But eventually we decided to go for this like end-to-end approach because it works surprisingly well. So for example, this like navigation task was solved like out of the box after like initial training. So robot more or less knows where to go in most of the tasks and so on. And pick and place also works for different tasks automatically from it. So yeah, we decided not to kind of focus too much on separate things and try to do it as much as possible end-to-end. But yeah, but definitely I would say we tried only like initial ideas that we had. So we had like much more ideas that we wanted to try, but we were very limited in time to implement it. And we like implemented the things that we believed most, and it was like more straightforward to implement. But yeah, I definitely think the results for this problem can be significantly improved. So what we did, we just scratched the surface, but it's really like nice benchmark. And I think like other researchers who will continue working on it, they will definitely achieve much better results by simply implementing ideas from the like recent papers and so on. So I definitely believe it's very far from the achievable result.
Yeah. Oh, we have a question from Ethan. Sorry if I mispronounced. Please correct me.
No, it's good. Great presentation, guys. This was really helpful. This is probably a question that Ilya is best positioned to answer. But previously you worked on your decoder only transformer. And one of the things you added in that was a look back. So you had the history of the last 2 frames or whatever, and then you did a far look back. And I was wondering, kind of conceptually, what do you feel like is the difference between using that look back and using a system 2 for this kind of context? What would you expect it to do well in, and what would be the pros and cons?
Yeah, it's definitely like good thing. And during the competition, I thought about that in this look back. The problem is that kind of the more you change and go farther from the original architecture of Pio 5, the like longer you will need to actually like train the model to actually achieve good results. Kind of the more weights you add, the more like changes you implement in the logic, the farther it goes. So most of the changes that we implemented, they're kind of very smooth because you can initialize them such as they like look exactly as Pio 5 looked before. And this was like one of the reasons why we didn't test it. And also it will take more time to train because now we need to process like multiple images and so on, and it will take like really some time. So there's probably more like resource and like training speed limitation why we didn't even try it in this approach. But I think overall, yes, it can help. If you, for example, look back for like, I don't know, 2, 3, 5 seconds and use it as extra input to a model, then these simple problems, for example, if model already seen that it's putting this radio back, it will continue like putting it on the table. So the simple things it will resolve, but there still can be like cases that it will not resolve when you make like very similar movements in the range of like 1-2 seconds in the very beginning and in the very end of the task. So yeah, like the short answer, I believe that using these old frames will probably help with the cases where this kind of very local, like nearest past information can resolve the problem. But it will not help with the cases when like very similar situation can happen like with like 5 minutes between them. So I think that the system 2 is more for higher level reasoning, for higher level planning. And again, we use like very simple system 2, so it's also maybe makes sense to just make estimation of the current stage for like longer time and somehow aggregated beta and so on. So maybe like partially it will already achieve these results. But yeah, it's more about like just short-term resolution and like long-term things.
Yeah, makes sense. Cool. Please ask the question.
Yeah, thanks so much for the presentation, guys. So, Ilya, you mentioned one thing you wish that you had more time to look at was reinforcement learning approaches, and like the things that come to mind for me are I'm not sure to what degree that Pio 6 went through and exposed everything that they're doing, but I'm curious like what methodologies come to mind for you. I know that out of Sergi's group, the dagger methodology is something that's really common for doing that, like for getting those correction trajectories. But I'm curious if you could expand on that a little bit more. Yeah.
Yeah,
Yeah, so
I think that.
yeah, okay, yeah, go ahead.
Thanks. I think that collecting corrections, so enrolling the model, and when it kind of fails, help it to recover and record this data, is very proven in the practical, in the real world domain method. So I would definitely use this if I would have enough resources to do this. And what we see in the last half a year for RL, which is do kind of similar, but in a more narrow way, kind of just very near what model already can do, slightly expanding it. It's probably already proven that this is working. So it's kind of a way to trade resources, either human or compute, to better quality.
Yeah, and I think like so we discussed multiple ideas related to RL in the very beginning of competition, when we kind of felt that we will have much more time. We even discussed, should we like, I don't know, assemble this controller that they are using for data collection, and should we like really do like Dagger and intervene and so on. Of course, we didn't do it. We didn't have time and so on. I think we also wanted to do like some very simple thing to kind of, for the task where we already have some reasonable success rate, just generate more trajectories where we successfully can complete the task. So basically, our model has a lot of randomness. So simply like rerunning the model from the same initial state for some like subtask where we generally fail can kind of generate more successful data. And even like retraining this data will just make our kind of distribution of the actions that we predict like much more narrow around the like correct actions. So we thought about these things. I think they're like most straightforward, probably not the most powerful RL approaches, but some simple things that we thought. I would say if we had like maybe like 1 extra month, this is probably what we would start. So either like rerunning model, having like rollouts on like some things that we can solve, but not always, and trying to do some Dagger, but it's also not so obvious how we can do Dagger without controllers. But I think that in the long run, of course, you need to use like some more powerful RL approaches and so on. And it's kind of very, very tricky thing usually to optimize. Yeah, I think so. Pio 6 also released like interesting approach where they don't use it as reward. They just kind of provide as an input, whether it's like good or bad rollout, and there are like many things how we can optimize the reward directly, or there are like some other approaches. So yeah, again, we didn't really try any RL here, so I cannot comment which one I think would work well or not, and it's very like trials and errors, I think, in this case. So yeah, like definitely it should help. There are definitely a lot of potential in it. I'm believer in RL in robotics and VLAs. I think it's probably one of the biggest things in 2026. But yeah, just need to try different things and see which one works for particular problems.
Yeah, if I'm not mistaken, that's exactly what's NVIDIA done. They perturb slightly initial conditions and kind of unroll the policy, perturb slightly initial condition that as they were in the training data set, unroll the policy, and if it was corrected, they add this into the training data set. So in this way, they basically start to expand data across the points that they already have. And we actually started to do RL. We train reweighting model, which is a reweighted model, which is put more emphasis on the episode which were shorter, which kind of are known heuristics to be of a better quality. But our experiment on only one tasks that we were able to conduct in the time don't show any definitive improvement, so we abandoned this.
Yeah, have you heard of stage-aware? Stage. It's out of Peter Abiel's group. Stage-aware reward modeling.
SMARM or?
Yeah, SARM.
Yeah. That was inspired by this model, by this approach. Like Justine, who's also working on in the beginning of our challenge, actually implemented value policy for behave, and you can in somewhere in the Discord, or I can share her GitHub how she done it.
Yeah, that would be great. Yeah, I ask all these questions because I'm working on something right now where we have some resources to do some of these things, and we're just trying to figure out exactly what the best things to try would be. So thanks for the feedback.
Cool. There is also a question in the chat from Key. Again, sorry if I'm mispronouncing that how VLM performance tied to VLA performance proficiency, and my slightly naive maybe understanding is that obviously the better VLM you have, the more you can do with action model train on top of this. But first of all, it's much more dependent on the actually training action data set. But even if they're the similar, why some VLMs are worse and some are better is that a lot of VLMs are trained to align image and language representation. So it's kind of classical clip architecture where the two parts of neural network, one processing images and the other processing language, should come with a very close embedding, close in a cosine similarity space, which is good for question answering. So if you ask such model, is there a dog in this picture? It would be good at answering, but it would be good, very bad at actually spatial understanding. So if you start to rotate this dog and move it around, it's actually would be a very hard job for such neural network trained on such data set to say, oh, it was parted, how it oriented, etc. Where the boundary of this object, especially because to answer questions, you don't need to know so much about boundaries. And even a long time ago, when I worked on self-driving, we saw such problems that even top VLM models, if you show them a picture of a road and there is a cycle lane and the cyclist not on the cycle lane, you ask them, is there a cycle lane? They answer, yes. Is there a cyclist? Yes. Where is the cyclist? On the cycle lane, because cyclists should be on the cycle lane. So it's kind of very bad at processing spatial information. And PolyGemma is known to be much better because Google, for quite some time, also use various spatial data to train basically segmentation and just object detection together with just language annotation to training the VLMs. But it's still kind of, you still need a lot of robotics data to fine-tune this visual encoder to pay attention on what actually important for robots. Nahib?
Yeah, I mean, you kind of partially said that, but yeah, I just wanted to add that I think there was I think someone from Gemini Robotics had like a keynote somewhere, I think in CVPR. So one of the hypotheses there was that if the VLMs are good at pixel level task, they're more suitable for VLAs. So essentially like, yes, segmentation or like the other forms of pixel level understanding.
And right after Malmo was released, Malmo 1, with the pointing capability. I don't know, this is kind of a funny anecdote, but Malmo was released for like CVPR is when it was kind of publicized. And then at ICCV, like a few months later, miraculously, Gemini became really good at pointing tasks. And so like those types of embodied reasoning tasks where it's like, it's sort of regression tasks, but in token space, is where I think you start getting that, like, you know, you start getting a lot of capability and like feature richness in the VLM that enables downstream tasks. Not to also jump in too much, but.
Yeah, but also like the interesting trend that there is this recent work VLA 0 that actually Gleb just couple weeks ago Gleb released this blog post where His couple more people actually re-implemented it with different VLM. And it basically what this work shown that you can use directly VLM as a VLA. You just don't need to change anything almost in architecture. You just use the actual like tokens for numbers as predictions for actions and simply fine tune it on the robotics data, and it kind of works, at least for some problems where it was tested. And again, so there are some couple of groups re-implemented it, including kind of Gleb. Who is here, so it kind of shows that it's actually like nice results. And I think, just want to add that I believe also that at some point, and probably pretty soon, whenever these new VLMs are trained, people will just start to add robotics data directly for the training data there. So you kind of, nothing stops you if your prediction for your VLA is simply the same tokens, same text tokens, just add a lot of robotics data to your VLM pre-training, and even, I don't know, all this biggest LLMs, VLMs, and so on, they will simply out of the box learn some physical world, some embodiment problems, and so on and so forth. So I think that VLMs will get much better soon when we just start pre-training them in robotics data from the very beginning. Because now the trend is mostly they're trained for different problems and then fine-tuned for robotics, but now there is not so many obstacles to actually include robotics data directly into pre-training or fine-tuning data sets for VLMs. So they will definitely get better. So.
Yeah, but I just want to highlight that you still need a lot of robotics data. So it's VLM can be enough as a VLA from the architecture perspective, but from the data perspective, you still need robotics data. And just for accuracy, the work that we released was from Robot Learning Collective, and Oleg and Sergey done most of the job, and my part was the most humble. So yeah, but we did show that we can just take small VLM2 in our case, and just ask it to produce floats that are directly floats as chars that are directly robot action, and worked quite fine. This idea was first proposed by NVIDIA in VOA 0, and we just replicated on a smaller scale. Great. Awesome questions. Thank you so much. I think we can stop here.
Yeah. Thank you guys so much for your presentation.
Yeah, thank you for this great session. Yeah, we went over like 20 minutes. That's really great. Thank you for your time. And yeah, I think Ilya is very late on your place.
Oh, yes.
You're in
midnight
Thailand
already. Yeah. Yes.
Oh man.
Right.
Okay.
Thanks again for inviting us. Hope to see everybody soon. Bye-bye.
If you guys aren't in the Discord,
Yeah.
come on.